we now begin with the team presentations where all the finalist teams will present their solutions to the jury members. Each team will have a fixed slot and we request all the teams to strictly adhere to the allotted time. We have 15 minutes max for the presentation and 5 minutes for the Q&A. Now I invite CDAC and SVNIT team. The team comprises of 2 senior scientists from CDAC Noida and 3 assistant professors from SVNIT Surat. This interdisciplinary team collaborated under the Voice Tech for All Hackathon initiative to design and develop a unified multilingual multi-speaker TTS system combining expertise in speech technology, research, system development and academic innovation. Now I invite the team onto the dais.
We are a team comprising of CDAC Noida scientists and academicians from SVNIT. So our title is a unified multilingual multi-speaker TTS model with one-shot speaker style transfer, which will be like explained why we are writing all of this. Okay. So so keeping it short, the motivation and all those things, the challenge is designed for under this motivation that the linguistic diversity of India is very high, and it's highly challenging to create scalable TTS systems. So we also like we have a famous saying like the dial exchange in every 10 kilometers in India. So for identifying the speaker specific characteristics, it also becomes challenging to design TTS systems which take into account the speaker characteristics, as well as so this challenge also comprised of many extremely low resource languages where many NLP tools or voice tools are not available. So under these settings, how we are going to design a TTS system which is reliable was the main challenge. So so our model, so there are major 3 strengths of our model. So we get away with the language specific phoneme systems while designing our TTS models, and we have shared parameter models, and with very minimal speaker data we can adapt to any speech, or we can clone to any speech and generate TTS systems. So the executive summary of our complete work is presented in this slide. So we are creating a multilingual TTS system which is supporting 11 languages, and other languages can easily be, other Indian languages can easily be incorporated into it. And this word error rate is less than 25%. So it's like whatever the TTS system generated, we also took a off-the-shelf whisper ASR and checked this. So the word error rate can also vary based on the ASR system which we choose. Like Indic ASR may be better for Indian languages. So, and we have a very fast system, and we also showed that the inferencing time is very low, and we can support like 6 requests per second. So the major technology integrates the bits model and free voice conversion. So it's a one-shot voice conversion which will be further be explained by Mukund.
Good afternoon, everybody. So this was the architecture that we followed. As you can see here, sorry. a user can give code mix text like today's meeting early hobe, so please jaldi aana, and that goes into our WITS model. In the reference audio, we extract the speakers embedding, and all the neutral speech and the speaker embedding goes to voice conversion module, and then we get the cloned output. So basically, this is a two-stage architecture. First one is WITS generating the neutral speech, and FreeVC converting the voice to your personalized output, you can say. So coming to the what basically vanilla WITS model is, basically it comprises of three basic modules. First one is the text encoder, which encodes the linguistic representation of the text. Second is the stochastic duration predictor and posterior encoder, which basically aligns the acoustic model with the linguistic representation. And finally, the hi-fi gain decoder, which synthesizes the representations into the waveform. So here, if you can see here, we have prepared a unified grapheme inventory of 500 characters. So in a way, we wanted to remove the dependency on phonemization of the transcript that we have. The voice tech challenge round had some of the low resource language like Magahi, Chhattisgarhi. For that, building a G2P tool was difficult. So we unified that grapheme inventory as they shared the same Devanagari script. And then we trained the WITS model. We also conditioned the language embedding as well as the multi-speaker embedding. So in a way, our WITS model, any speaker can speak any of the language. Means Bhojpuri speaker can speak English text also, Bengali text also, and Kannada also. So as per the challenge rounds requirement, we need to convert the voice into a personalized output, you can say. So we used a FreeVC module, which is basically a one-shot voice conversion. It extracts the speakers embedding from the reference clip, as well as the neutral speech that came out of WITS model, and it injects the reference clips embedding into the synthesized audio, and the cloning of that audio is happening. So a data set, this was also a good thing about our model, that we used the least amount of data set. Despite English being in the loop, which is not truly phonemic, which is phonemic in nature, we used around English 49 hours of data, which was sufficient for a grapheme-based unified model for English. Rest of the Indian languages said are basically orthophonemic, so we can leverage that advantage. So we can say 30 to 40 hours of data for English is sufficient, means for a decent text-to-speech for English. For other languages, the data is sufficient. And the infrastructure was thankfully provided by CDAC Param Siddhi. We trained our model on NVIDIA A100 GPU. And the total duration of our training was only 1.5 day. So using the grapheme based model, you can, this model becomes very simplistic. You can take that speech TTS corpora and just inject it into our training script, and your TTS will be ready. No specialization required for linguistic annotation or phonemization. So this one is the test we did on our test set. That's the male substral distortion score. And you can see here the MCD score for Hindi is 3.97. That means the generated audio is very much almost similar to the ground truth. But that was not in the case of English and Gujarati. Obviously, phonetic mismatch was there, but still 4 to 9 is considered to be a good score in MCD. And in another objective evaluation, we used Whisper ASR for calculating the word error rate, means intelligibility of the synthesized voice was measured using Whisper ASR, and English obviously had stronger support, so 9% was approximately 9% was the word error rate. Marathi had the least support, so we were at 22% of the word error rate. So this can be attributed that Whisper ASR has the little bit support for other Indian languages. Yes, and this speaker similarity means the reference clip that was given to us and the synthesized voice in that. So how much it was similar. So as you can see, almost the cloned voice is 86 to 91% same. So we can say free VC module effectively transferred timbre and prosody. Yes, this is one of the important aspect while means going to a research project to deployment. For that, we did some benchmark testing on a single NVIDIA Quadro RTX 6000 series. This is a very basic GPU with 16 GB RAM. We also wanted to test on RTX 2080, that the beginner level of GPU. So on that, our max throughput was 6 requests per second, and the throughput and the mean latency for concurrent user, you can see here. Okay. Is up to 8 user making 2 requests in a second. That our this GPU and this machine can and this model can handle 8 into 2, 16 requests without latency. Up to 16 user, you will get a latency of 4 seconds. But I think 8 to 10 users, it can easily cater a concurrent request. So, yeah. So these were the few takeaways of our approach. Unified grapheme vocabulary that makes it phoneme free, and we completely removed the dependency of G2P converters. Zero sort adaptation using free VC, and finally the lightweight architecture, which basically separates the linguistic modeling from speaker style transfer. Future roadmap. So we want to extend it to support dialects and extremely low resource languages, especially from the Northeast region. And obviously, you'll see in the demo also, most of the systems are not expressive, so incorporating emotion and speaking style control directly into the synthesis. Robustness, fine-tuning FreeVC to reduce timbre leakage and handle noisy reference audio. These and the final one, that edge deployment. So far, we have been able to reduce the model size to 70 MB. For Hindi, we have tried out, and now we are trying to incorporate again all the 11 languages into a single model with a total model size of 300 MB. I think that would be good for edge deployment. Yeah. And yes, one thing that TTS requires is text normalizer. And for Indian languages, we do not have text normalizers, handling of numbers, web expressions, emails. There are so many nuances in there. So we completely rewritten the text normalizer part, and that makes the TTS more smoother. It can speak the numbers, decimals, and everything. So that was all from our side.
Any questions from the audience?
I have one question. In the voice conversion, are you training the voice conversion model also?
No.
So it is the frozen model is what you're using.
Yeah, yeah.
So it's basically cascaded setup, right?
Yes.
Right. So our WITS model can work in separate. We have designed it in stage phases. No? Stage 1, stage 2. So stage 2 can be removed. And still the WITS model would work with 11 of the speakers' voice. You can interchangeably use it.
So does it work like even if the reference audio that we are giving in the voice conversion, if the reference audio is in a different language and the generated audio is in a different language, so still the speaker can be picked up?
Right.
Yes.
That can be picked
up. And any accent transfer is happening, or just the speaker is getting picked up?
Only the timbre and the tone of the speaker is being captured. Yeah.
Okay, thanks.
I have two questions. One is, you said you have 500 units in your graphene. So if you have 11 languages, and it's almost like 50 units per language you're taking, right? So what is the reduction that you've done? Because normally, if you look at Indian languages, total should be 50 units, not more than that. So why did you have 500 units in your system?
You can say, ma'am, time and the effort that would go into making a common level set kind of thing. So we actually didn't do, and obviously the model parameter certainly increased when we increased the parameter to 500. But certainly this is a very good idea, and after this challenge round, we will make a common level set kind of thing and map each language character with a common label.
Yeah, another question that I have is, you said you have a duration predictor. Prosody, does it include only duration, or are there other parameters that you need to worry about?
I didn't get your question, ma'am.
You talk about prosodic transfer. You said there is which has an inherent duration predictor.
Right.
Is duration the only parameter that is responsible for prosody?
So in prosodic transfer, as far as I know, like only duration is not the thing. Like there are many things like pauses and pitch, all those things. In this model, we are not capturing. We are only capturing the timbre and tone, nothing else.
Yeah, I know. One other thing is, when you train with multiple languages, and if you synthesize for a new language, what will happen is if you give multilingual text, code switch text if you give, it will speak one speaker's voice and another speaker's voice, the other language will come. Right. So how do you hope to address this? It will not give the same voice because after all it's some context vector which is there somewhere.
Yes, right.
And that context vector is seen in Gujarati, this text. So if the new text that you have, that phrase is Gujarati, like you speak like the Gujarati voice. If something else is Telugu, like you speak like the Telugu voice.
Yes.
Have you see, it's very common. So how do you hope to address these kind of problems that are there?
If it is a totally new language we are talking about, ma'am?
Yeah,
means the model has not seen
that language at all. This is what often happens. Because you claimed that it can work for any new language. That's
it can work for new language with minimal of training from that language.
How did you do text normalization for English? You converted it to Devanagari or something. What did you do?
No.
Kept the script as it is.
So, the script as is, but the numbers are handled differently. So, different kind of like a URL or an email or a number or a date. So, usually in TTS systems, the numbers are not properly pronounced.
No, but there is in Python, there is a package which does number normalization.
Yeah, that is there, but it doesn't work for many Indian languages. It works for English. We have tested.
It works for most Indian languages.
Yes.
You just have to augment that, that's all.
Yeah.
Num2 words is a
it's for English.
Yeah. So we thought it will speak 1 million and 10 billion kind of words, right? We wanted it to make.
Use it, and you have to just augment it for all the languages.
So we wanted it should speak 10 crores, like in Indian style. So that obviously that can be that is usable.
What you are suggesting, like we can augment the same thing, or we already had one number conversion, that's why we use it.
One last question as we have to move to other presentations.
Yeah. So you mentioned at the end that there is a dedicated one-time normalization task which you have to perform because of the Indian languages, and I totally understand and acknowledge that it is not available. The system is not yet matured. But don't you think that that will act as an overhead with respect to, suppose if I want to take it to a common person as a scalable parameter which can scale to billions of people in India? So even though it is one time, but don't you think that so my question is, how lightweight with respect to the compute overhead do you think that your solution is going to be? Suppose if I want to scale it to, because here we are talking about the pregnant, like the underserved pregnant women, the aam admi or the very underserved people, which so we should be really compute less intensive, right?
Yeah.
So
So I'll try to answer this question. So the text normalization which we have uses standard Python libraries. It doesn't it hardly gets computed in milliseconds. So it's not like a model. It's a rule-based system which works well, which doesn't incur so much overhead in terms of computing or time efficiency.
So we were thinking in a code mix text, we want to introduce the context of the, suppose there is a word and written in between of Hindi word, but rest of the text is code mixed with English and Bangla. So we wanted to identify the language there also. So it's another overhead. So, but if it makes the TTS generation more natural or intelligible, then a few milliseconds of overhead can be taken up. Because as I shown, 0.52 was the mean latency. So after before normalization, it was only 0.51. So an additional of 0.1 millisecond was the overhead in the rule-based system that we developed. Thank you.